This is an introduction to thermal management for XP and MX Xlamp LEDs. Welcome to the training module on thermal management for XP and MX Xlamp LEDs. This training module will discuss the thermal management for the XP and MX families of Xlamp LEDs. More and more high-power LEDs are applied into different lighting applications as they present many advantages over traditional light sources, including high energy efficiency, producing high-quality light, extremely long life, inherent rugged structure, directional light output, environment-friendly, and infinite controllability. The Xlamp MX series LEDs provides up to 130 lumens for cool white and 107 lumens for warm white at 350 milliamp. The Xlamp MX LED can also reduce luminaire and lamp manufacturing costs through an increased shelf life with reduced moisture sensitivity and the smallest warm white bins in the industry, enhancing LED to LED color consistency. This series LEDs can provide better design options for indoor applications, including under cabinet, retail displays, LED light bulbs, and fluorescent replacements. The Cree Xlamp XP series product line offers 3 options in a common footprint. This series delivers high light output and efficiency for a single die LED. The Xlamp XPG is available in 4 white colors and can be driven up to 1.5 amps. The Xlamp XPE comes in 10 color options and can be driven up to 700 milliamps. The XPE package is available in 3 color temperatures and can be driven up to 500 milliamps. Drive current should be considered when choosing an LED component, as it will affect the light output and the light engine's overall efficiency. The Xlamp XPC has a 110 degree viewing angle, the XPE has a 115 degree viewing angle, and the XPG has a 125 degree viewing angle. One of the most critical design parameters in LED illumination system is the system's ability to draw heat away from the LED junction. In basic operating relationships, increasing forward current will increase LED's light output, and high forward current increases forward voltage, which results in higher power. The higher power dissipation raises LED's junction temperature. High operating temperatures at the LED junction adversely affect the performance of LEDs, resulting in decreased light output and lifetime. The maximum junction temperature for each product line is specified in the product datasheet. In order to properly manage this heat, specific practices should be followed in the design, assembly, and operation of LEDs in lighting applications. The most important consideration for successful thermal design is to minimize the amount of heat that needs to be removed. It is important to separate the LED drive circuitry from the LED board so that the heat generated by the driver will not contribute to the LED junction temperature. The next most effective strategy is to minimize the ambient temperature inside the fixture. This goal is achieved by paying attention to several design parameters, such as conservative packaging design that does not allow the upper limit on the overall system power density to be reached. Maintaining clear and clean airflow paths for natural convection cooling is vital as well. Enhancing thermal conductivity between the heat sinks and the LED is very preferable for thermal management. Even though the heat removal from the heatsink is via convection, the path from the LED to the heatsink depends upon conduction. Finally, the orientation of the LED PCB heatsink should be considered carefully. It is important to position the board heatsink so that the plane is vertical. If the board plane is horizontal, it will block the formation of air convection currents and substantially reduce the cooling capability of the system. All Xlamp LED packages have an electrically isolated thermal pad. The pad provides an effective channel for heat transfer and optimizes thermal resistance from the LED chip junction to the thermal pad. The pad is electrically isolated from either the anode or cathode of the LED and can be soldered or attached directly to grounding elements on the board or heatsink system. Heat is conducted from the LED package through the thermal pad and on and into a PCB, which should be mounted to a heatsink so as to transfer the conducted heat into the operating environment. Cree offers one solution to enable the use of FR4 circuit boards over metal core circuit boards in certain illumination systems. We will study on it in the next few pages. FR4 is one of the most commonly used PCB materials and is the NEMA designation for a flame retardant, fiberglass reinforced epoxy laminate. A byproduct of this construction is that FR4 has very low thermal conductivity. An expensive way to improve thermal transfer for FR4 PCBs is to add thermal vias, plated through holes between conductive layers. Vias are created by drilling holes and copper plating them, the same way that a plated through hole or via is used for electrical interconnection between layers. Adding vias in an appropriate way will improve the thermal resistance of an FR4 board. The use of vias underneath LED thermal pads to dissipate heat through an FR4 PCB and into an appropriate heatsink. Here we present the results of thermal performance simulations conducted by Cree. Let's look at thermal dissipation without vias in the left chart. It shows the thermal resistance varies with a different thermal pad size. The thinner the FR4 board, the lower the thermal resistance becomes. The right chart shows the effect of various diameter and number of vias. The result is the larger the diameter of the via, the lower the thermal resistance becomes, and increasing the number of vias shows considerable improvement for small via diameters as well. Because LED junction temperature will affect LED lifetime, Cree conducts other thermal simulation and thermal verification tests on the LED board assembly under real-life conditions. It is concluded that a copper-filled via has lower thermal resistance than a solder-filled one through the simulations. Cree recommends creating areas of 10 mil vias set up on a rectilinear grid of 25 mil. The reasons for this choice are for the combination of performance and manufacturability, and when used with 2-ounce plating solution, it can be reliably filled with solid copper as part of the board plating process. The figure shows FR4 board for the Xlamp XP package.